All right, today we're going to do chapter 3, section 4, the multiplication of whole numbers. We'll finish up the chapter, not today, well, next week, because all we have left is division. These are all taking a long time because there are a lot of examples, a lot of algorithms. So that's why I apologize. It's taking a long time. What exactly is multiplication? And when would you introduce that in school? In your own words, don't try to read for it. What is multiplication? Because you have to understand, again, you have to understand algebra to do all this stuff. If you haven't taken algebra, even if it's not in your lesson plan, I would strongly suggest taking it, because nothing's worse than being an instructor in front of the room and not knowing how to do the problem you're putting up there, or how to answer the kid's question. So when they ask you, what is multiplication? Why do we do it? Why do we need it? Don't
Like a lot of numbers you can add, you can try it out.
Where'd you see that?
Oh no, I'm just like saying.
Multiplication is turbo addition. Yes, that's exactly what it is as you see in the picture there, if we had 5 times 4, what that means is one of two things. Is we have 5 4s, so we have 4 plus 4 plus 4 plus 4 plus 4, or it means that we have 4 5s. 5 plus 5 plus 5 plus 5. They both mean exactly the same thing, which we'll go into now. We're going to talk about later on in our properties. So 5 times 4 either means 4 plus 4 plus 4. So add 4 5 times. Or put 5 plus 5 4 times. The way we describe it, we have 4 here 5 times. How do you read that? 5 times 4. So it's not a happenstance that it's the same words we use. 5 times 4 or 4 times 5. So that's what it means. Then we have to look at, how do we teach that? Before you go any further in your classes, you have to make sure all the kids know how to do addition. If they can't do addition, they'll never do this, because it's just it's a faster process. But then we get to problems when we have multiple digits. It's easy when you have one digit each side, but once we have multiples, that's where we have to have some plans on how to approach this. And there are a whole bunch of shortcuts that I'm going to show you all that you may or may not know. So let's look at the definition of multiplication. According to our sheet, it says for any whole number n, or a, it's different they're doing, and natural number n, a times n is equal to a plus a n times. So that's the formal definition of it. Okay, I have a question here. What is a whole number? What is a natural number? Infinity and natural numbers? From 1 to what? Infinity, right. Now, does it matter that the n is a natural number? Why? What is 0 times 0? 0. So we could do that. The reason we do that is because n represents the number of items you have. Actually, the number of items you have. If it's 0, you don't have any items, so it's nothing there. So again, those are the type of questions your kids are going to ask you, and whatever you tell them may stick with them forever, and that will look bad later on. Let's look at some examples here, or some processes. We have arrays. What is an array? You have computers, I bet. An array is, and start off with the computers, is an array is how you allocate a location of memory for a specific piece of information. It's the same as a storage location. Think of a file cabinet or a library bookshelf. Typically, what people do is they start storing books on the top left and keep on going. So this is the first row. This is second row, third row, fourth row, fifth row. And these are the locations. So let's give these letters, make it easier for us. So this is A, B, C, D, E. If I wanted to know what this book is, then I would go, what is C15? What do you think that means? Go in the C row and go to the 15th book. And that's what it is. It's exactly how computers store information on the hard drives. And you've seen them before, as the examples there is if you order donuts by the package, you have 2 rows and you have 6 donuts across. And so how many donuts do we have? This is the first row. This is second row. So we have 2 here and we have 6 there. So 2 times 6 is 12. So once we have a set array of same size rows and columns, then we can tell exactly how many elements we have in that position. Eggs, if you ever buy them by the 24 carton, you have 6 across and you have 4 rows. So you have 6 across and you have 4 rows. So 6 times 4 is 24. Whenever you have an array, it's always the number of rows times the number of columns. So when I'm saying a 4 by 6 matrix or an array, then we know we have 4 rows, 6 columns. Now, how is this going to help us do multiplication? Very much so, yes. Because then you know what you're talking about. And that's why whenever you are able to put things in nice location and a nice formatted setup, it makes it easier for the kids to see. And it also makes it easier to teach them subtraction. How would you teach subtraction there using this information?
Say, don't try to subtract 500. I'll just teach them to cross out each one by 1, 2, 3, 4.
That's too much work. Is there a shorter way? What's that?
Circle 5.
Okay, but then you're not teaching subtraction, you're teaching addition. It's 5 plus 5 plus 5 plus 3. Well, we know we have how many in each column? How many rows do we have? We have 4 rows. How many in each row? There's supposed to be 5. So 4 times 5 is what? But in the last one, we're missing how many? So if we're missing 2, then we know we have 18. Or then we can teach them. You always teach kids with a method they know first. You're right. I would go by 5 plus 5 plus 5 plus 3 because they know addition. Let's look at subtraction. How many are we supposed to have and how many are we missing? Because subtraction is the absence of items being there. So looking at arrays, it's not included in there, but here's, for example, if we had 23 times 41. You don't want to draw that many items. So how can we use arrays or matrices or arrays to make it easier for them to learn? Because by now they have to know how to multiply the smaller numbers. So the first number, 23, there's the tens, there's the ones. 41. So 2 times 4 is 8. 3 times 4 is 12. 2 times 1 is 2. 3 times 1 is 3. Now, if we add straight up and down, well, since this is a 1 here, you can only have one number per box. That comes to the next box over. So 2 plus 3 is 5. And then 8 plus 2 is 9 plus 2 is 13. Is that right? What should it be? Let's look at the way we would do it. So it's supposed to end in the 3. There's a big difference. So how can we use this box to help this? Remember the lattice method. What was the lattice method? We have 2 and 3, 4 and 1. So 3 times 4 is 12. 3 times 1 is 3. Two times 4 is 8. 2 times 1 is 2. What do you do next with the lattice method? We add the diagonals. So this one becomes a 3. 2 plus 0 plus 2 is 4. 1 plus 8 plus 0 is 9. 943. So you could use the lattice. Remember, we introduced the lattice method in the addition. There's another way we can do this using lines. So how would you represent 23? So that's 2 lines. And then 3 is made up of 3 lines. Four, 1, 2, 3, 4, and 1. All we have to do is add up these intersecting points. This uses the lattice method. We add diagonally. So there are 3 dots here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's a 4, carry the 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. 943. This method, I've noticed that helps kids do multiplication a lot faster because they can see it much readily. Actually, it'd be easier if you sit on this side because I'm going to be in your way half the time. It also works for bigger numbers. Let's look at 123 times 34. Remember, you could keep it rows and columns if you want, because when you show them the arrays, they have rows or matrices, you have columns. So we have 1 row. We have 2 more. Make sure you have a break between there so you know they're different numbers. And then you have 3. The next one, we have 3 columns. And then we have 4 columns. So we have 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 3, 4, 5, 6. 3, 4, 5, 6, 7, 8, 9. So you take them by diagonals. The upper corner and lower corner have to be by themselves, and then put them in diagonals from there. So this first one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's a 2 and carry the 1. Or you could put it over here. I could put the 1 over here. Because it still makes it 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So it's going to be a 2, carry the 2. 1, 2, 3, 4, 5, 6, 7, 8. And then 3. So the answer is 3, 8, 2, 2. Any questions about this method? Another thing the kids are going to get confused about. Unlike addition and subtraction, multiplication is the only operation that has multiple symbols. What are all the symbols for multiplication? We have the X. We have the dot. What else? You can have them in parentheses, right? That's an exponent. That's a different thing. I'm talking about when you look at it, you know it's multiplication. The operation is multiplication. But that's good. Yes, we'll talk about that in a second. Or nothing. There's nothing between these. Which is what happens here also. Multiplication is the only operation that doesn't have to be there to be there. Not in the early grades, but in later grades, you're going to introduce variables. That's going to be your next hurdle, is introducing variables to students. So many parents say that once we got into letters, I lost math. Because math is supposed to be numbers. Yeah, for the early elementary school, you do have just nothing but numbers. But then you have to introduce variables, because now you have to make up equations. So what does this mean? How do you read that? We read that as 3x. What it really means is 3 times x. It's just that you've seen it for so long that it's second nature to you. When you look at it, you know what it means. It's just there. But that's the hard part about being a teacher. You have to break down what's second nature to you to people who don't know anything about this. Because you're starting in the much more difficult range because these kids don't even know numbers. You got to introduce all this. You have to build everything. And when you're teaching elementary school, that is the most amazing learning process ever. Because whatever foundation you give them there, that builds them up from there. If you ever ask elementary school, what's your favorite kid? What's your favorite subject? What do they always say? Math. If you ask any elementary school kid, what their favorite class is, they said math. Why? Because manipulatives. They get to play with things. You have your number blocks. I mean, if you want me to, I could bring some manipulatives down here. We can play with them, or we don't have to. If you want to. Okay, I'll bring some next time, and so we start learning how to do these. Well, actually, after we finish division, the class after, I'll bring the number blocks, and we'll start looking at how to do all these. And yeah, that's a good idea. We'll do that. But yeah, I have to show you guys also how to use manipulatives as well. Which again, I in the past I haven't done that because if you're but you're right. It's if you actually physically hold it and touch it and move it around, you know what the kid's going to go through. And I still remember when I was a kid, we used to have wooden number blocks. They were all different colors, which I can still picture it. Me playing with these little small blocks and got to these big cubes, and I was so fascinated by playing with them that I don't remember learning much about math. So yeah, your first time is let them play around them in centers, learning about just how to play with them. And then once they learn how to play with them, then they start learning, hey, let's look at this stuff now. And in other words, make everything into a learning experience for the kids. You mentioned the X. You mentioned the X, and that's what we're talking about. The X is a cross. Some people call it St. Andrew's cross because it was invented so many years ago. What does the word product mean? Well, product means multiplication. Yeah. Yeah. So that's what I'm saying is, so now we're using a cross product, something like 3. They used to read that 3 cross 5, but that would call it just 3 5, 3 times 5. And the tough part about using that symbol is depending on which level of math you're at, this could mean 3 times 5, or in matrices, it means 3 rows, 5 columns. And there's a level of mathematics where we use that as a cross product of 2 large sets. But in this level, it's just multiplication. Well, let's look at this. 3 times 5. That's exactly what it means. If we introduce them to the arrays, it's 3 rows of 5 blocks each. Again, this is how you'd use manipulatives. So by this time, again, you see how important it is to have addition skills. So 5 plus 5 is 10. 10 plus 5 is 15. So the stronger their addition rules are, the faster your multiplications will go. How would you introduce that concept to kids? Using manipulatives. See, again, it blows my mind. We look at this number, we know what it means. What do you think it means to a kid? An 8-year-old, 9-year-old kid? Not much, really. Is so how would you break down 23 into smaller numbers? So it's 20 plus 3 times 4. So 23 is 20 plus 3. So how do you represent 20 using manipulatives? This is the ones column. This is the what? The tens column.
2 rows of 10.
Yeah, two long rows. Was you're right. 20 is 2 times 10. There's two tens numbers. And then so that's what 23 means. What does times 4 mean? We would have 4 sets of 2s. There's 4 of those. And then 4 sets of 3 blocks. And then what would you do?
So group each have like place values, so you do a once area first, you would add everything together, and then go to the 10, and then together, and then you get the 2 big numbers from both.
Very good. Let's say, yeah. Either have them count them, or you're right, since arrange them. So you know that you only have either ones, tens, or hundreds. So I would take these, have them put them all together until they get one big long one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to have 2 leftovers. That's this. We have a 10 with 2 left over. So then we add up all these, the long ones. We have 1, 2, 3, 4, 5, 6, 7, 8, and this one. So we have 9 long ones and 2 short ones. And that's exactly what 23 times 4 means. Now, the problem is, at what point do you cut them away from manipulatives? That is a tough call, because you eventually have to get to a point where you have to be able to show them a numbers and have them do it on a piece of paper themselves.
People think multiplying like singular numbers, like
Yes, yes. Always push the singular numbers first. The smaller ones. I mean, think about it. What numbers, and I know they're all, you all could do it, but what numbers are hard to multiply together? Well, in the single digits. Sevens. Actually, I'll show you about the nines. I'll show you that one pretty quick. Yeah, pretty much these. Fives are pretty easy. Fours, threes, twos. So yeah, these, you notice how it stops after 5, it starts getting more difficult, because teachers, when we're growing up, they didn't spend much time in those numbers. But let's look at nines. We're base 10. So 9 times 6. Put your fingers up. Put down, starting from here, put down your 6th finger. So 1, 2, 3, 4, 5, 6. How many fingers do we have here? How many here? So 54. 9 times 3. Put down your 3rd finger. We have 2 and 7, 27. 9 times 9. Put down the 9th finger. We have 81. So 9s are pretty easy. So that kind of stuff. You get it now? Yeah. So once you see that, I wish I would have done that. I don't know if I saw it. I was just playing around with YouTube, which I spend most of my free time. And I remember seeing that many years ago. So that's so cool. I think I see that as the kids more often.
Helping them make the like the times table. Do you remember?
Yes, I was gonna say, yes, exactly right. That's exactly right. And I remember as a kid doing that. The teacher giving us this blank sheet with all these numbers on top. Also 0. On your desk?
That's like every single problem that I had, I would make them. And like that, I would make them all the way up to 10. And like that, like, I had to make them again, but the problem is like, I didn't do it.
And yeah, we'll get to that one. We'll get to the digits next, because that's the next part the kids have trouble with, is anything over 9. Because then once they understand what tens are all about, then it gets, then you have to build it to 20s and 30s, and that's the next hard part you'll have. And then this side here, we do the same thing. So it's 0 here, 1. Because then this is what you can use to start teaching them some of the properties of math. What are the properties? Okay, we have these in the middle, the diagonal ones. 0 times 0 is 0. 1 times 1, this is the multiplication table, is 1. 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9. Oops, I missed it. 9 times 9, 81. Okay, those are the ones that you want to work with first, the doubles. Because that's a good place to start. Because remember, they know addition or subtraction. So look here, if they know 5 times 5 is 25, then 5 times 6 is 5 times 5 plus another 5. We have to have 6 5s. So you go 25 plus 5 is 30. So yeah, they can do that. Right. It's a safety line for them. But then here's something even more cool, is you only have to do half of it. 2 times 8 is what? 2 times 8 is 16. It's a mirror image. So what you're going to teach there, now you're going to teach them that, let's call this row A and this is row B. Now you can teach them that A times B is the same thing as B times A. 2 times 8 is the same thing as 8 times 2. That's the commutative property. As long as you have the same operation, I can move them around. So then now you don't have to have a big square piece of paper anymore. All you need is a little triangle. Makes it smaller. You can put it in the corner of your desk instead of the whole corner. But a lot of people don't see that. They insist on working through and do every one of these boxes separately. Just do one and then pretty much fold it over and copy it over.
And if I make it have it, like, they don't have to like do every single number unless the problem requires it. Then
Yeah, because yeah, you cut the time in half too. So yeah, then once you show that to the kids, say, "Wow, that's saves." But yeah, have them do the whole one first. And say that takes a lot of time. Okay, let's do it halfway, and then you can show them that. You notice that this number here is 5 times 7 is 35. That's the same thing as 7 times 5. So again, that introduces another one of the properties. We have to talk about the properties as well. Commutative is the first one we talk about. So that's why, again, you start that using addition. Does commutative property work with subtraction? Why not?
Take that, 5 times 3 is 2, because I'll put 3 minus 5.
Does not equal, right? This equals 2. This equals, since 5 is bigger, it's negative. 5 minus 3 is 2. So when you teach subtraction, I know I should have this the other class. When you teach subtraction, I mean, go off script a little bit. Addition of signed numbers. Invariably, everybody uses calculators. Computers do not use subtraction. They use the addition of negative numbers. And that's the way you introduce it also. If I had 5 minus 3, how would you use the number line to teach them that? Yeah, I don't have it from the room, but yeah, we go some number. So we go to 5. 5 is from 0. You go 1, 2, 3, 4, 5. Now this thing says, since it's a minus, it says change direction. Go 3 more spaces backwards. 1, 2, 3. So that's the way you introduce subtraction to kids using number lines. Because again, subtraction is changing direction. It's adding a negative number. Because whenever you start off from where you end and you count some more, that's addition. You're adding onto that, but you're going in the wrong direction. Which is exactly what subtraction is. Subtraction doesn't really exist. 5 minus 3 is actually 5 plus negative 3. Because negative 3 is this long. If we're doing measurements, it's this long. So I go to 5 and I measure the negative 3 distance. I'm now here. So that's what we're doing. Yeah, we'll get the manipulatives. I'll show you how all this stuff works. So here's how you should teach them. If the signs are the same, use the common sign and add the numbers. If the signs are same, use the common sign and add the numbers. That pretty much sums it all up. 2 plus 5 equals what? We know it equals 7 because they're both positive, so the answer is going to be positive. 9 plus 3 is going to be positive 12. How about negative 2 minus 4?
2 plus 1.
Well, they're both negative, so the answer is negative. 4 plus 2 is 6. Whenever you do math, do the signs and the numbers separately. The problem students will get into is when they try to rush it. When they try to do too much at one time. The numbers and signs, and then you have the plus and minus signs and equal signs and dividing line signs. Too many signs everywhere. So if you treat everything separately, the signs first and then the numbers. Negative 8 minus 1. They're both negative, so the answer is negative. Add the numbers. You teach them that, and that will help them so much. I mean, I have adults that are now in my algebra classes and above that said if they were known that, they would have not made half the mistakes they did. Because the negative signs are the parts that hurt your grade. Because you're going to change signs. I've done it a lot of times when I do my examples. I've been thinking, I'm talking, I'm writing, and I forget a negative sign. Or I change a plus to a minus. So be very careful with signs. So that's the first rule. If the signs are different, if the signs are different, take the sign of the larger number and subtract the two numbers. When I say subtract, I mean larger number minus smaller number. That's what we talk about, subtract. So 9 minus 5. Is the answer going to be positive or negative? Yeah, because 9 is positive, 5 is negative. 9's bigger, so the answer should be positive. What is 9 minus 5? -3 plus 8. Is the answer going to be positive or negative? Because 8's bigger than 3, the answer will be positive. 8 minus 3 is 5. -7 plus 4. It's going to be negative because 7 is bigger than 4 and 7 is negative. So now we go 7 minus 4. Two minus 9. Which number is bigger, 9 or 2? 9's bigger, 9's negative, whatever's in front of it. So it's negative. 9 minus 2. 7. Once you see it that way, calculator is not really needed for this kind of operation. But if you were taught that many years ago, you wouldn't have made half the mistakes you did. So again, it's these two rules here, and it does the same thing with multiplication division. We'll also talk about those. All right, so let's continue back to the lecture of multiplication. The cross product, we're going back to the cross product. Like A cross B. A and B can be sets. In other words, A can represent capital letters, A and B, and B can represent the numbers 1, 2, 3. What this one represents, the cross product, we know how many solutions we're supposed to get. We have 2 elements there times 3 elements there. So it's the cardinal number of A times the cardinal number of B, which is 2 times 3. We're supposed to have 6 answers. So what the cross product here represents is everything in this first set has to combine with, has to multiply with everything in the second set. So A and 1, A and 2, A and 3, B times 1, B times 2, and then B times 3. Believe it or not, you go through this kind of stuff every day. Just getting dressed. Let the first set be the shirts. The second set be pants or dresses or whatever. And then third set you can have with shoes. Do you ever think about, okay, what should I wear? What kind of shirt? I have my blue jeans. What I'm going to wear with what I'm going to wear with it? Or this t-shirt, this t-shirt, this shirt. So you go through it all the time. You go through all these possible combinations and you pick the one that's least objectionable, the most favorable to you. So you do that every day. So the Cartesian product, that's what we just talked about. That's the cross product. So sir, let A and B be finite sets. What does finite mean? Finite simply means it has a number. It's not going to infinity. Like the number of students in this classroom right now is finite because it stops at a specific number. So the cardinality of A, remember what these represent? What does that little n represent? It stands for the number of elements in the set. So the cardinality of set A equals little a, some number. The cardinality of set B is a little b. The total number of possible combinations of set A and B is denoted by that. Which is the same thing as saying the total number of the cross of those. Now, the reason it's the Cartesian product is because Rene Descartes invented pretty much the lattice work, the matrix work. So it's named after him. Either Cartesian product or the cross product means the same thing. properties of multiplication of whole numbers. What's the closure property? What does the closure refer to? Remember from addition and subtraction? What does closure represent? Closure means that the sum, or actually the operation produces a number that is within the set of numbers used. The reason I say operation is because we have addition, subtraction, multiplication, division. We know addition satisfies the closure property. Because if we said that set A and set B are both elements of the whole numbers, that little e means elements of. So A and B are made up of whole numbers, 0 to infinity. Is addition closed under the closure property, under the property? In other words, if I add two numbers that are whole numbers, will they give me an answer that's also a whole number? Yeah. If I add two numbers that are whole numbers, the answer has to give me a whole number. How about subtraction? Is it closed? Is it a closed operation? Why not?
Because you can also not get with and get the negative number.
Very good. Because it's not closed, because 4 minus 9 is -5, and this is not a whole number. It's an integer. Is multiplication. Yeah, because if we start off with 0 times 0, that's in the whole number set. 1 times 0, all that stuff, and then 9 times 9, that's in the set. So yeah, it's any two numbers multiplied together will also give me another number that's in the whole numbers. Is division. Well, yeah, what if we have are decimals in the whole numbers? No. So some of them are, some of them aren't. Like 4 divided by 1, it satisfies, it's in the whole numbers, but 4 over 5 isn't it? So you notice that all of these are paired off as one's yes, one no, because they're inverses, they're opposites of each other. Now let's go back to multiplication. So closure is the first property. The second property is commutative. Is commutative a property of multiplication? In other words, if I have A times B, is B times A the same thing? Yeah. 3 times 4 is the same thing as 4 times 3. We saw that with the number square. They both equal 12. Is the associative property satisfied under multiplication? The associative property introduces parentheses. So is multiplication closed under, so this one is A times B times C, the same thing as A times B times C? Why not? How do you mean?
Well, it really,
I guess it's like, let's say A is 1 and then B is 2.
Okay,
And C is 3.
let's say 2 times 3, 2 times 3 times 4, like that. 2, 3 times 4. 2 times 3 is what? 6 times 4 is what? 3 times 4 is 2 times 12. Associative property multiplication is a thing. Because if all the operations, if all the numbers are let's look at this, 2, 3, 4, 5, 6, 7, 8. If I gave you those numbers there, how would you multiply them? Yes, I know most of you just start from left, work your way right, but you don't have to. You can pair off these numbers however you want to, whatever makes it easier for you. For example, 4 times 5 is what? That's 20. 2 times 8. 3 times 6. Times 7. Now we can go this way. Now we can just start going left and right. It's going to give us the same answer no matter how we do it. So because of the commutative and the associative property, I can pick whatever numbers I multiply if they're all multiplication. By the commutative property, I can move them around, which means I can multiply whatever numbers I want to first. It becomes more apparent with this example. 3 times 4 times 5. Which side is easier to do using this property? Yeah, because 3 times 4 is 12. 4 times 5 is 20. To do this one, all you gotta do is 3 times 2 is 6 and put a 0 by. This one, 5 times 2 is 10, carry the 1, 5, and then all this other stuff. So that's the purpose of this whole property, is I can pick which two I multiply together first. Which brings us also, because up until now, the associative and distributive property, the commutative properties, always separated addition and subtraction. They all have to be addition or they all have to be multiplication. You can't combine the two. The distributive property does just that. This one combines addition and multiplication. So there's our example. The number out in front of a parenthesis or in front of a variable is called a coefficient. The purpose of the distributive property, one of the purposes, to remove the parentheses. What we have to do here is whatever the coefficient is, what operation? What is A doing to X plus Y? Multiplying. Because this is A times, so every coefficient is multiplication. So A times X is AX. A is positive times positive is positive. A times Y is AY. So it got rid of the parentheses for us. And now we can go further with our operation. And that's going this way. We can also go backwards, which is called factoring. What do AX plus AY have in common? They both have an A. If I take out the A from both of these, whatever's left over goes inside parentheses. What's left over? Yeah, the X, the plus, and the Y. Once I take out the A, it's gone. I pretty much, when you factor it out, this is what it looks like. AX plus AY. They both have an A in common, so I take it out. Whatever's left goes inside the parentheses. In other words, since I took out the A, I'm going to divide both of these by A. What do I have left? X plus Y. And that's what goes inside here. So whatever you factor out, that goes in front. And then you divide everything in there. And whatever's left is your answer. The identity property of multiplication. So what times A gives me A? What times a number? So 3 times what gives me 3? Well, you could, but then we haven't even talked about division yet. 1. So anything times 1 is itself. It keeps its identity. And then we also got the last one is called the nullity property of multiplication. A times what gives me 0? Yep, 0. So anything times 0 is 0. Check out the distributive property. Ooh, yes. You've seen this before in math classes. X plus 3 y minus 5. Have you seen this before? What is it called? What kind of operation is this? How do you solve it? Everything's order. Yes, that's a safe answer. Good answer, but it's a safe answer. Everything's order of operation. Remember what FOIL meant? It's an acronym for first, outer, inner, last. So the first terms in both of these equations, multiply them together. So x times y is xy. The outer ones, this x times, so positive times negative is negative. X times 5 is 5x. So this is xy. This is negative 5x. Inner ones, positive times positive is positive. 3 times y is 3y. And then the last ones, positive times negative is negative. 3 times 5. And then you combine if you can, which you can't. That only works when you have binomials, two numbers inside the parentheses. Anything larger, you can't use it. So what we use now, remember we just talked about the distributive property. The distributive property works here. It's the same as this concept. Here's a parenthesis. Whatever's in front does what? It multiplies to everything inside there. So here's the number in front. It multiplies times y. It's a positive in front. So positive times negative is negative. So x plus 3 times 5 is 5x plus 3. Now we have smaller ones. We have a coefficient, so we multiply. X times y is xy. Positive times positive is positive. Y times 3 is 3y. Negative times positive is negative. 5 times x is 5x. Negative times positive is negative. 5 times 3 is 15. Here, we have the same answers. We get the same answers. And you first teach them this because it follows the distributive property. Because if you think about it, x times all this is the same thing we just did here. 3 is, we just changed the format of it. It gives you the same answer. Another way we can use distributive property. is by using blocks. So we have 2, 3, 1, and 5. So this is 2 times 1. This is 3 times 1. 5 times 2, 3 times 5. We did this before. I mean, it's not anything special. So we have 2, 10, 3, and 15. So 15 is 5, carry the 1. 3 plus 10 is 13, plus 1 is 14, so it's 4, carry the 1. 2 plus 1 is 3. So the answer is 345. Exponents. What are exponents? Yeah, exponents are the little number on top. What does an exponent mean? Yeah, it tells us the number of times the base is multiplied to itself. This is the base. The base is 3. Exponent is 4. So it says I multiply the base to itself 4 times. 3 times 3 times 3 times 3. 3 times 3 is 9. 3 times 3 is 9. 9 times 9, 81. How would you write that? X times X times X times X. It doesn't matter what the exponent is. And we have a whole bunch of properties. We had a number A raised to a power n times a number A to the power m, where m and n can be or doesn't have to be the same number. Since the bases are the same, we just add the exponents. Let's think about it. If we had 3 squared times 3 to the third, this one means 3 times 3. This one means 3 times 3 times 3. We have the same base and it occurs 5 times. So it makes it much easier just to add the exponents. If we have 2 numbers raised to the same exponents inside parentheses, we can distribute those. If you have fractions in the same bases, whatever's on top minus whatever's on the bottom. So for example, 3 to the 5th minus 3 squared is 5 minus 2 equals 3 to the 3rd. But if you had more on the bottom than the top, a negative exponent simply means that this number now goes to the bottom and changes its sign. The negative exponent does not make the answer negative, it simply changes its location. The negative exponent doesn't make the number negative, it simply changes the location. One last thing real quick. I know you guys have to walk across 10 miles of walking. I apologize. Those last one. Any number raised to 0 is what? Think about it. With what we just learned, what equals 1 in mathematics? In fractions, what equals 1? Always in fractions. Anything over itself. 5 over 5, 1. So anything. So I can have a to the power n over a to the power n. So the last rule we just learned is, since the bases are the same, what do we do with the exponents? We subtract them. When we're dividing, you subtract. When you divide, you make things smaller. So that's why you subtract. What is n minus n? 0. There's a proof. There's our first proof in mathematics. Let's see here. That's pretty much it. Yeah, we covered everything else except the last part. We'll have to deal with the number blocks. I'm sorry again. I'm so sorry that I'm keeping y'all late, but I got into a groove and I started talking too much. Sorry. All right. Have a great weekend.